Okay, thank you very much for the invitation. It's fantastic for me to be in St. Petersburg. I always wanted to come. The first time in Russia, and you know, I sort of forgot all my Russian that I learned in grade school, but it's still I've always wanted to see the city. So I want to first talk about random. Well, the title of my talk is Random Matrices and Random Schroedinger Operators. And so let me just first talk about random matrices. So, you know, random matrices were probably first introduced in the 1920s by statisticians, especially a Scottish statistician called Wishart, who wanted to understand, you know, covariance structure of large data sets. And you know, you sort of try to understand the covariance structure of large data sets by setting up some model which has typically normal random variables, and then you look at, say, the sample covariance matrix, and that's sort of the first example of a random matrix. There's still many open problems that connect to Wishart's work, but in mathematics and physics, it was really first considered in the 50s by Wigner. And Wigner's idea was that he wanted to model the behavior of energy levels of large nuclei. So you take, you know, some big uranium or plutonium or something, and you look at the energies. And when you look at this, you know, it's a point process. It's a set of points in a line. And when you look at them, you see that they repel each other. And Wigner had this idea that you know, to understand it, we really need a good mathematical model. But what is a good mathematical model? So, you know, opinions vary. Of course, I think physicists would not agree with Wigner what his idea of a good mathematical model was, because he just thought, I don't care what the mechanism is. I just wanted to be simple, and I would like it to replicate this repulsion. So that was basically what he wanted to do. And he had, you know, a couple of tries. So actually he started with some strange random Schrödinger operators that didn't work. And then he looked at some tridiagonal matrices. They also didn't quite work. And in the meantime, you know, he deduced this Wigner semicircle distribution that is so famous. So it was kind of a series of papers in the Annals of Mathematics. And the last one, which he sort of arrived at, is this, you know, Gaussian orthogonal ensemble, or Gaussian unitary ensemble. So, and that sort of seemed like it really was simple and replicated the repulsion. So what is it? Well, you know, it's sort of just a simple symmetric random matrix. So you take a matrix and fill it in with IID normal 0, 1 random variables. Okay, in this case real, and in this case complex. Sorry, complex. So let's call this matrix, I don't know, M, and then you just symmetrize it. So you look at the additive symmetrization, or m plus m star over 2 over square root of 2. And so this is what's called the GOE or GOE model. So let's say this is n by n. And it's not so hard to see that if you look at this random matrix, it has some random eigenvalues. They live on the line. And the way they look like is they go from roughly -2 square root of n to about 2 square root of n. Not exactly, but typically. And there are n of them, and they live here. And you know that if you draw kind of a histogram, that what you see is the semicircle law. That's the famous Wigner semicircle law. And you can even write down the joint distribution function. So they kind of look like they would want to be Gaussian. So there is e to the minus sum of lambda I squared. Okay, this would be just the Gaussian product measure. But then they notice that they actually want to be Gaussian with a constant variance, not a large variance. So they're really forced to be big. And the way they are forced to be big is by Vandermonde. So lambda I minus lambda j, product of I less than j. Vandermonde vector, and there is a power here, beta, and this beta is equal to 1 in the case of GOE, and beta is equal to 2 in the case of GOE. Okay, so one of the things that you can see from right away is that the probability, even in the finite case, so that the probability that you have two eigenvalues in an interval of 0 epsilon, okay, is what? Well, typically it would be, if these points are independent and just dropped according to some Gaussian, it would be something like epsilon to the power 2. But because of this repulsion, you get an extra factor of beta. Okay, so something like this. So let me put it like this. So this is an asymptotic as epsilon goes to 0. Right? So this extra power of beta here gives you repulsion. Now, this is kind of these are finite models for this repelling structure between the eigenvalues, but somehow you would like to take out the finiteness of the problem and get some kind of essence behind this process. And the way to do it is to take a scaling limit. So you can take a limit of this eigenvalue process. So let's call it the set of points lambda n. Okay, and so you can say that as lambda, if you look at lambda n, and you blow it up by a factor of square root of n, okay, then you're zooming in to the middle of this process, okay. You remember that you have n eigenvalues in this interval of length roughly 4 square root of n. So if you want to see, if you want to take a limit in which you actually see points and not just some density or something, then you have to blow it up by a factor of square root of n. Okay, and so this is a random point process, and then this random point process converges in distribution. Okay, so in distribution as n goes to infinity to some limit. Okay, so this we call the sine beta process. Okay, and you could think of this sine beta process again as sort of the essence of the random matrix eigenvalue process. It's a process of points on the real line. Okay, and this is a translation invariant. So in distribution, that is, if you take a sample of it and translate it by 5, you get something with the same distribution. And so this convergence, by the way, is called the Einard method theorem in the cases beta equals 1, 2, and 4. And we proved it with Benedek-Walko for general beta, that there is such a limit, and there's a characterization of this limit. Another nice thing about this,
Whose method theorem?
Einard method, I think.
Arbitrary beta is not related to random matrices. We're talking about this Dyson gas? Or?
Yes. Yes. I'm talking about this thing. So the next question is, I mean, one thing that is nice about these eigenvalues is because you have repulsion, there is some kind of order. So typically there is this interplay, but because these guys don't like to be close to each other, they sort of find a place where they're relatively orderly. So one way of measuring it mathematically is by looking at, so let's call this sine beta process, let's call this lambda, okay? And you can look at the probability that there are 2 points. No, actually not that. Let's look at the probability that there are no points of this capital lambda in an interval of size 0, of length lambda, right? So this kind of quantity, if it was just a Poisson process, it would give you, this would be exponentially small in lambda, right? It would be actually exactly equal to e to the minus some constant times lambda. But in this case, this is actually something much worse. So the probability of having a hole is something like exponential of minus lambda squared times some constants, okay, as lambda goes to infinity. So these are just two properties of random matrix eigenvalue distributions that that are nice to know. This repulsion and this this repulsion and that gap probability. Now, let me tell you what happened with this idea of Dyson about random matrices. Basically, in the 50 years since it was introduced, or even almost 60 years that it was introduced, in the physics literature, there were born lots and lots of models where people believed that you will see this kind of eigenvalue distribution. Okay, there is a paper from about 10 years ago where there are 20 different models. And all these models have some reason. There's some justification, and some of them physicists would even consider a proof that you have this kind of random matrix eigenvalue distribution, but none of them had actually a precise proof. In fact, the situation was much, much worse until about last summer, or 2 summers ago. Namely, even though there was this belief that almost every disordered system in some phase will have random matrix distributions, we couldn't even tell that random matrices had random matrix distributions. More precisely, if you did the same thing, except instead of putting here normal variables, you put some other distribution, say Bernoulli or I don't know, whichever your favorite thing, we couldn't tell that then if you look in the limit, you will still get the same process. Okay, and last 2 summers ago, there are 2 proofs of this by 2 groups of people within about 2 weeks of each other, and actually quite different ones. So it's a very active area now.
So this is a universality in a different sense than Johansson's.
No, it's the same as Johansson's, but it's much more general. So Johansson handed.
It was only Gaussian variables.
Yeah, he did Gaussian divisible random variables, and now it's known for fairly general cases. So if you put in here, I think now with very mild conditions, if you put something here instead of normals, then there is a proof of. Actually, the 2 groups. One is the first ones were Erdős and Yau and Schlein, and the second group was Tao and Wu. Terry Tao and Wu. Now, let me just tell you some examples that is expected to have this limit. So one of them is this Bohigas et al. Conjecture. So what is it? So you have basically a domain, okay, and you do it so that the Sinai billiard is ergodic. It's a very simple one. Is you just take a square and remove a circle from it. So you look at this domain between the square and the circle, and you suppose that you take a quarter of this, just so that you don't look at multiple eigenvalues. So it's just this right triangle, or it's an eighth of that, right? This right triangle minus a little bit of a circle, and then you look at the Dirichlet Laplacian. Okay, so this is a deterministic operator, and it's well known that it has discrete eigenvalues. Okay, and it's believed that if you look at the right place in here, you will see GOE distribution. In fact, there's a paper from the 80s where they studied the gaps at certain sections of this part, and it looks like that the distribution of the gaps is really like that of the GOE. But there is no proof of this. This is a big mystery. There is it's really far from being solved. And you see, notice that there is no randomness here, so you have to introduce some randomness in order for this to work. So you have to sort of look at the random position. Right? So that's one conjecture. The second conjecture is probably you know all this. It's called the Montgomery conjecture. So Montgomery conjecture says that if you look at so you look at the zeta function, and so let's say this is 0 and this is 1/2, right? And let's say that you look at its non-trivial zeros. Okay, so let's call that process Z. Okay, so let's call that process 1/2 plus IZ. Okay, so that Z is a set of points on the real line. Then what is believed is if you look at Z and translate it by some uniform random variable, let's say this is uniform in 0, 1, and we multiply by T or N or whatever, so that you translate it by a uniform amount. Okay, so and then you have to blow it up because these Riemann zeros, they get dense. So you have to blow it up by a factor of log n. And it's believed that you see this was deterministic, but now we looked at the random place. So it's now random. Okay, it's a randomly shifted deterministic process. So it's believed that this converges to sine 2. Okay, and this is the Montgomery conjecture. And there are some partial results in this direction. So there are certain test functions which, if you integrate, they do converge, but there are only a few of them that you know. So let me introduce the next model, which is the Anderson model. Okay, so mathematically there is some nice physics behind it, but I don't know that, so I just tell you the math. So the Anderson model. Mathematically, the idea is the following. If you look at the adjacency matrix of a path, okay, so let A be the adjacency matrix of a path like this. Okay, so you know this is of length n. Okay, so A is just this matrix which has zeros here, and then ones below and diagonal. So it's also called the discrete Laplacian. Then one thing that you see here is that it's, if you look at the eigenfunctions of A, well, they're basically you can compute them exactly. You know, you have seen this in many math classes, right? They're basically just cosines with some frequencies sampled at discrete points. Okay, so you take some cosine, I don't know, and then you just you sample it at these points and these discrete points. And so in particular, what you see is that they live everywhere. Right? The eigenfunction doesn't concentrate to a particular section of this line, but they're sort of spread out at the whole spread of the line. Okay, so this phenomenon is called delocalize. Okay, or extended, or this is one. Now there is another kind of different picture where you take a matrix, let's call V. Okay, where V, say, has a diagonal matrix. I don't know, just put some diagonals, V1, Vn, and this is a Vi as our IID with some distribution. Okay, so then if you look at the eigenfunctions of this, of course the eigenfunctions are really concentrated at well, the eigenfunctions are the coordinate vectors. Okay, so that's clear. So the idea is to see what happens in between, right? So you have, in this case, where the eigenfunctions are all spread out, and in this case where the eigenfunctions are all coordinate vectors. So you're interested in what happens if you look at A plus sigma V. So it kind of sort of like a constant times a convex combination. So what are the eigenfunctions of this like? Okay, and so as you imagine, right? If you vary sigma, if sigma is very small, near 0, then the eigenfunctions will be like that of A. If sigma is huge, then the eigenfunctions will be like that of V. So they'll be sort of localized with some kind of decay. But what happens in between, and where is the transition? Okay, so that is sort of the question. So where is the transition? Okay, so let me tell you what was known before. So in 1D, what is known is that the transition is about sigma equal to constant over square root of n. Okay, so that's how much should be the variance in order to, if sigma is much bigger than that, then the eigenvectors will be all.
What do you mean 1D? Numbers instead of matrices?
Okay, so this is 1D because it was a line, and you can of course do this for a grid or a high-dimensional grid. Okay, I didn't say that, but so you could do it in any dimensions. So in 1D, this is at about c over square root of n. So if you have sigma significantly bigger, then you'll have eigenfunctions that are localized, significantly smaller. You'll have ones that are spread out like this. Okay, and then you also know that.
Strictly speaking, in a finite system, there's no sharp criterion for the transition. Transition can only be defined sharply in an infinite system.
Well, that's.
And then there's no transition. That's what we believe.
But you know what you're saying. What you're saying is kind of less precise. I mean, because you know this kind of thing that the transition is here. It doesn't really appear in the infinite system, right? Whereas in the finite system, you can define this very well. But I don't want to. Sure. So one thing you could look at is the you could look at the L4 norm of the eigenfunctions, right? So you use some of the squares of the fourth powers of the entries, and if it's spread out, then that thing can be small. If it's localized, then that thing will be very big. So you can just put a threshold, and then this is what governs that behavior.
It doesn't decrease smoothly; it just jumps from here 0 to b.
No, it doesn't really jump, but you can always, you know, and this level it doesn't jump, right? If you want to jump, then you have to go to the infinite system. Yeah. But you can still, you know, you can still define a threshold, right? And in this case, so actually in 1 dimensions, when you look at the infinite limit, and that's what I'm going to talk about, there is even at the infinite system there'll be a smooth transition. But you'll have to see what the infinite systems are looking at. Okay? Yes.
Know that the eigenfunctions are spread out?
Yeah, the eigenfunctions, you know, they're just like products of these in the different directions. So.
And V is the same.
V is the same. Yeah, it's just diagonal. Okay, yeah. So V has as many random variables as there are vertices here.
Yeah.
Okay, yep. Okay, so 2D. Okay, I'm not going to talk about 2D. 3D. It's probably the only case you care about, right? But 3D, so the following is believed, okay? The following is known, okay? So instead of having to divide by square root of n, you don't have to divide by anything, okay? So the idea is that sigma is greater than some constant. Then you have localization. And then the belief. This is you know, this is a very, very hard math problem that you know, there are some proof-like things in physics, but they're really, really far from being rigorous. Okay, so the belief is that for small sigma, you have delocalization. Okay, and this is actually 3D and higher. In 2D, the opinions vary. So there's some people who think that the same thing happens. There's some people who think that you have to divide by something else. So you know, this is very exciting. I have no idea. But something converging to infinity.
Localization for which sigma is proved.
Yes, that's true. Yeah. So right. So this actually is proved for every D. Now, what I want to say here is, yes, just 1 second. So the only case, right? The only case where delocalization is known. So a 3D and higher is believed to be true, and it's known that this kind of thing happens on trees. So if you have a regular infinite tree, then that kind of thing does happen. Whatever you mean, or if you approximate an infinite tree the right way. Now, what I first want to talk about is the 1D case. Okay, and actually, instead of just looking at eigenvalues, at eigenvectors, I want to first tell you about here what is the belief about eigenvectors. Okay, about eigenvalues. Sorry, so eigenvalues. Okay, so let's say if the eigenvectors are localized, then in many cases it has been proved and it's believed that it's generally true. Is that you have that the eigenvalues, they look Poisson. Okay, so what does this mean? Right, you look at this model, you look at this matrix A plus sigma V, you look at its spectrum, you see these points. Okay, in this case it goes from something like -2 to 2 roughly, and you look at some place, some location, and you zoom in so that you see a process. Okay, so you have to blow it up by n in this case. And then the statement is that when you do that, this converges to a Poisson process as n goes to infinity. Okay, and this is proved in many cases, but not proved in many other cases. For example, in 1D, when you put Bernoulli, this is not known.
Homogeneous process.
Excuse me.
Homogeneous process.
Homogeneous process. Yeah, this is.
What is the parameter?
So, you know, in 1D you can pick sigma to be a constant, say. Okay, so when D is so when D is greater than or equal to 3, then what you believe, and you have delocalization, then it is believed that these eigenvalues will convert to some kind of GOE distribution, so a random matrix distribution. And there is absolutely nothing proved about it. This is one of the cases of this Wigner universality. So this is belief. Okay, and then I'm going to talk about D equals 1. So I will talk about what happens in the critical case. And then let me see which one did I left out. All right, when sigma is small, so when sigma is very small, so really you're extremely delocalized. Okay, so it's even more delocalized than here. Then you expect to have some kind of Poisson, some kind of periodic distribution. Okay, so you just have like a random translate of Z. So that's roughly the picture. So, okay, let me tell you about some results that we have in this D equals 1 case, and then I want to tell you about some results for D equals 1 plus epsilon. Okay, and they're of very different nature. Okay, so these things are due. This is joint work with Benedek Walko, actually Eugene Kryczewski, who is at Toronto with us, and Benedek Walko, who is at Madison. So let's see, what is this theorem? Theorem is the following. So let me change notation here in the middle and replace sigma by sigma over square root of n, because we're talking about actually sigma over square root of n by sigma, right? Since you're talking about Am I doing that right? Yeah. Yeah, sigma by sigma over square root of n. Yeah, that's right. Because we're talking about the one-dimensional case, and that's kind of the right picture. Okay. So the variance of these variables will be now sigma squared over n. So let's lambda star be an element of let's put it like this, 0 to 2. Okay, and let lambda n be the eigenvalues of, what was it, a plus sigma over square root of nv, right? And let's say that these vi's have variance ones. So then the following holds. So you have to look at this lambda n. So remember, this is this set of points from -2 to 2. Sorry about that. Okay, and here you pick a point, pick a window lambda star, and you look what this point process looks around lambda star. So how do you do that? You subtract from this lambda star. Okay, and then you have to blow it up by some factor. It's actually 1 over 1 minus lambda star over 4, and then also n, so that you see a point process. This will actually make it. This will make this point process. Let me see if I did it right. No, you need a square root here. Yeah, so this will make a point process of this, which is approximately of density, a constant density. Okay? So this will converge in distribution as n goes to infinity of some point process, which I call z tau. Okay, so this is the point process. Actually, in order for this to be true, I have to add the random phase. So let's say that u plus. So I'm going to randomly shift this so that it will converge to a u process. This is an independent uniform. On 0 2 pi, okay, because this thing is going to be 2 pi, roughly 2 pi periodic. So it will have roughly 1 point in every 2 pi limits. Okay, so this converges to this point process, z tau, where tau is a parameter. Okay, so tau is a parameter, and it depends on two things. Well, in fact, I can tell you what it depends on. So tau is equal to so sigma squared over 1 minus lambda star squared over 4. Okay, so it's one parameter. The limiting point process depends on one parameter, and it's a true parameter. So these various point processes that we get here really depend on the tau, and they're not just images of each other. And this, but it's only one parameter. So somehow sigma and this lambda star, which is where we're looking in the spectrum, they combine to give one number, which will determine what kind of process we get. And so what is this z tau? So this is a point process, and so let me just say a few things. So it is a point process. So this is translation invariant. Actually, it's not ergodic. It's interesting. Well, I had to be a bit more careful about that, so it's not completely. Okay, let's just forget that for now. So it's translation invariant, and you know it's on the real line. And what you're really interested in is how is this point process related to random matrices? Right? We have taken this critical one-dimensional Anderson model and took a sort of limit of the eigenvalues of it, so does this look like a random matrices or not? So let me tell you a few points. So one is if you look at the probability that there are that there are no points in 0 lambda in z tau. Okay, so what is that? Well, it turns out that this is exponential of some constant, and then you have e to the you have lambda squared over tau minus. This is as lambda go to infinity, and tau is fixed. Okay, so the repulsion of not the repulsion, the probability of gaps, of being huge gaps, is just like a random matrix. They really don't like lots of gigantic gaps. And well, the next thing is, if you want to ask about repulsion, okay? So if you look at the probability that there are 2 points in 0 epsilon, so this was the thing that I was most excited in, because I was hoping that you would get a kind of random matrix value with some beta. Okay, so I was really, putting my epsilon, and then I was hoping to get here a factor. But in fact, it turns out that this is. Let me write it just for this way. You can even that the repulsion is much stronger than in the random matrix case. So more precisely, the repulsion is epsilon to the minus log epsilon, so some constant. Let me put it like this: c plus little o 1 as epsilon go to 0. Okay, so it's much smaller than epsilon to. It's much more unlikely to see 2 points close together than in the random matrix case. So how are these things proved, and then what can you do with them? Well, first of all, let me just tell you how this process is defined, this z tau. Okay? So I will define this process for you, because it has a simple definition. Okay, so let me see what I need for that, and then after that I'll explain in a few words of how you get this limit here. Okay, so the process. Okay, so one way of defining it is using this picture called the Brownian carousel. Okay, which is the following. So you have the following data that you start with. So you have here, this is the hyperbolic plane, okay, of Lobachevsky and Boyain Gauss, I guess. Okay, so this is a hyperbolic plane, H2. And in this hyperbolic plane, you have a hyperbolic Brownian motion. So there's an intrinsic Brownian motion that kind of converges here to a boundary point. This we call B. Okay. And so that's one piece of data. The second piece of data is you need a point on the boundary here. So let's say that this is the Poincare embedding, so that I can call that something. So let's call that point e to the IA. Okay, where A is uniform on 0 to pi. So it's a uniform point on the boundary, okay, independent of the Brownian motion. And now you do the following. You start with this point, which is a fixed point. Let's call it 1. Okay, and you move along this Brownian motion path at speed lambda. Okay, so first of all, you fix lambda. And move along this Brownian motion path at speed lambda. Okay? And, well, actually, sorry, move along the Brownian motion path at speed 1. Okay? And as you move along this path, you rotate this point on the boundary at speed lambda. Okay? But where do you rotate the point? Well, you rotate it about yourself. Okay, so if you're here, the rotation speed, of course, depends on where you are. The actual rotation speed on the circle depends on where you are on the Brownian motion. So there is an ODE that describes this. It's very simple, right? It's just, I hope I got that written down somewhere. Right, so I guess if you call this, if the point is if the point is e to the I gamma, okay, with gamma 0, e to the I gamma t, gamma 0 is 0, then you have the ODE, which says that gamma prime, the derivative of gamma in time is just lambda, so this is the speed of rotation, and then you have to have to use the fact that you're rotating from this point where the Brownian motion is and not from the center. So you could say it by putting in the Poisson kernel at Bt and the Poisson kernel from Bt to your point, so e to the I gamma. Okay, so that's the ODE. Okay, so what does this define you? So this defines you a function, gamma t of lambda, right? For each t and all lambda. Okay, it turns out that in t, it's still a differentiable function, and it's nice, but it doesn't have very many derivatives. But in lambda, this is actually analytic. Okay, so this is an analytic. Okay. And then you're looking at, so z lambda, z tau is just the following. So you look at when gamma tau, okay, that's where the tau comes in, is in some multiple, is at a. Okay, so when you hit this point, e to the IA, so you take two translates of this. So you're looking at when this angle is at a or 2 pi or some 2 pi times an integer away from a. So basically you're rotating this point at the boundary, and you're looking at when it hits there. Okay, and then you have to blow this up. Let me see. Yeah, so then you have to divide it by tau, I think. Is it right? No, you have to blow it up by tau. Okay. Okay, so let me say this again. So you have this Brownian motion, and you move along this Brownian path, and you rotate this path in the boundary, and then you look at the time tau when it is at this random point e to the IA. Okay, and for those lambdas where it's at that random point, you will have an eigenvalue. Okay, that's how you define the z tau. So this is equal to tau times the set of lambdas, such that gamma tau of lambda, I just write the same thing, or maybe write it like that. So e to the I gamma tau of lambda is equal to e to the I A. So it's kind of, people have been pointing this out to me, that this whole process is a little bit like SLE, except of course simpler, because it's just. But there must be some connection that that I think nobody has found that, because here you have an evolution of a boundary point which is given by some kind of Brownian curve inside the domain, whereas for SLE you have a Brownian motion on the boundary which gives you a curve inside the domain. So the roles are kind of switched in this case.
Can you from boundary point can you construct a full Brownian curve in some reasonable manner?
That's a good question. I don't know. I don't know.
Because from the speed of the point, you would know how far inside you are.
Yes.
So in a sense, you know the argument, but
yes.
the origin would sort of be implicit from the speed.
That's right. So you sort of you can reconstruct some kind of one-dimensional projection of it, but I don't know if you can reconstruct the whole thing. I would guess yes, but I never thought of this. It's a good question. Okay. Are there any questions about this? No. Okay. Okay. So.
Is your gamma T infinitesimal fractional linear transformation?
Well, gamma is just in this setup, gamma is just a number. Okay, gamma is just so the point that you're rotating here is e to the I gamma, and gamma is just the angle of the point in this representation.
This rotation around Born center
but
linear vector transformation.
Yes, so. Yes, so that is true. So if you look at, if you're looking at this gamma as a function of a new parameter, which is not here yet, but you could put the starting point as a parameter, okay? Then it would be true that this is a linear fractional transformation that evolves over time. So in fact, the way you can get this picture is from kind of a Brownian motion on SL2R. So what I want to show you is how to get this from that picture, okay? Because I think I already told you enough to have this statement proved. Okay. So let's see. How is this related to the Anderson model? That was up there. So you take the Anderson model, and you write down the eigenvalue distribution. You take a limit, and you get exactly this set of points and distribution.
So you did not explain, right?
I didn't yet explain. No. Okay, I'll get to that. But before I explain that of how you get this, right? Let me just see how this is useful for deducing these Repausian pictures. Okay? So yes. So. Okay, so just 1 second. Okay, so if you have 2 points in 0 epsilon, right? Then the following has to be true. It has to be true that since I have seen 2 points in this interval, remember if I take lambda to be 0, then I'm not rotating anything, so I'm just staying here. And if I take if I increase lambda, of course I rotate more and more. So if I see 2 points in our point process in 0 epsilon, this implies that gamma went around at least twice. Went around at least once. Okay, so in particular, gamma of tau, gamma tau of lambda of epsilon is greater than or equal to what is it? 2 pi. Because I had to go through at least had to make at least the first circle, and a full circle corresponds to 2 pi. Now. So what is this gamma tau? Well, remember, it's this Poisson kernel. So the derivative is lambda over this Poisson kernel, and the Poisson kernel can be bounded by 2 over the max, 1 minus the max of bt in this. So this is a max of BT in the Poincare disk. So this Poisson kernel can be bounded by that. So this gamma tau epsilon is certainly less than or equal to epsilon times that thing. So this is max of BT 0 t less than or equal to tau. Okay, this is just a trivial bound on the Poisson kernel. So well, okay. Now, if you want to just get this formula that I had up here, you have to think of this Brownian motion not as something in the disk, but this is in the hyperbolic plane. So remember that the hyperbolic distance is equal to. So let's say the max hyperbolic distance from 0, right, is equal to the following. Well, you can just write it in terms of this m. It's just the standard formula for the hyperbolic distance, which is a log of 1 plus m over 1 minus m. Right? And this is certainly greater than or equal to log of, let me see, so I want to make it log of 1 over 1 minus m. Okay, and in this case, this has to be greater than or equal to this log of 1 minus m. Let me see. Yes, it has to be greater than or equal to this thing. So it's log of, what do I have to write here? 1 over pi over epsilon, I think. Okay, because of this inequality. Okay, so what does this say? I have this Brownian motion in the hyperbolic plane, and if I have 2 points in this interval 0 to 0 epsilon, then the Brownian motion in the hyperbolic plane in a time tau, in a short time tau, have to go farther away from the origin than this number. Okay. So what is the probability of this? Okay. So the probability of this event is, well, you know, for short times, the Brownian motion in the hyperbolic plane behaves pretty much like Brownian motion in the Euclidean plane. So the probability of this is just you know, just like a Gaussian tail. So you can make it as exponential of minus that distance squared. So log pi over epsilon squared, and you probably want to put here a tau. Okay, and so this is the end of the proof. This is basically the idea. Okay, so why is this? How do you get this kind of strange picture with this Brownian carousel? So I want to tell you a little bit about that. So it's actually quite simple. So when you write down this, you write down the eigenvalue equation. For a plus sigma v. Right, so you have an eigenvalue equation that this is equal to something like a plus sigma v applied to some function psi is equal to lambda psi. Right? Then you can certainly write this in terms of transfer matrices, right? So you can write psi L plus 1 over psi L. So is equal to some transfer matrix which looks like, let's see, 1 minus 1 0, and here you have sigma VL minus lambda, or maybe the other way around. Let me see. No, lambda minus sigma VL minus 1 phi L minus 1. Right? So what is this? You've probably seen this before. So this is a tridiagonal matrix, right? And this equation, every row of this equation gives you an equation with finitely many terms, right? And if you want to get that equation, you can just read off the first line of this transfer matrix evolution. And the second line of the transfer matrix evolution is just a triviality. Okay? Just tells you phi L is the same as phi L. So it's a way of encoding this eigenvalue equation here. And then you can also check. So this is kind of a recursion, right? And you can solve this for each lambda.
So we'll go line by line or diagonal by diagonal?
You go line by line. Yeah.
Line by line.
Right. So you start with some pair of phi's. In fact, I'll tell you what. And then you can solve it line by line as you go on with lambda. So every time, and how do you solve it? Well, you start with some vector here, and you just keep multiplying with this matrices. Right? So if I call this TL, right? Then there are some boundary conditions which translate to the following. Right? It translates to the following. So lambda is an eigenvalue. And only if you look at T and T1, okay, and you apply this to the vector 1, 0, then you get something which is a constant times the vector 0, 1. Okay. So remember these things. So these things all depend on lambda. I didn't write it there, but it depends on lambda. So lambda is an eigenvalue if and only if this happens. Okay? This is just checking what the boundary conditions are at the first equation and the last equations, which are a little bit different from the others. Okay, so it's an extremely simple representation. Now, what one would like to understand is so if you call ML to be TL T1, so this is this kind of product of transfer matrices, then one would like to understand this evolution. And ideally, you would like to take a scaling limit of this evolution. Okay? So goal is to find the scaling limit of of ML is this process, right? 0 less than or equal to L less than or equal to N. But there is a first.
But do you want the sigma to be scaled by square root of n still?
Yes, it will be. It will have to, right. So in what scaling limit, right? This is a good question. So in this case, right, sigma. So the noise is like sigma over square root of n. Okay, so that's what you would like. And the eigenvalue and lambda should be some fixed lambda star. Okay, so let's call it lambda tilde. Let me put the lambda tilde here. Okay, so that we're looking at some plus lambda over n. Okay, so this tells you the window that we're looking at, and this lambda over n is exactly the scale that we have to move in order to see a point process in the limit. Okay, so this is how much. This is the right amount of motion. So this kind of scaling limit. Now the obstacle, well, you see, this is a matrix evolution. You're multiplying matrices. And you would like to, so it's some kind of, in fact, what it is a random walk, right? It's exactly a random walk. You take a group, an SL2R. For every fixed lambda, it's just a random walk. And you're hoping that this random walk will converge to Brownian motion. Okay? But of course, like this, it's not going to converge to Brownian motion. And the reason is that it's not, these steps are not microscopic, right? When n goes to infinity, this matrix that we're looking at doesn't converge to an infinitesimal matrix, right? It converges to some matrix which we call T star, as n goes to infinity, right? Which is just the matrix lambda star minus 1, 1, 0. Okay? So this evolution is not going to be microscopic in the limit, which is a problem. You can't take limits. So what you can do, though, is you can study the QL, which is you take this evolution and remove the macroscopic part. So you look at T star, so the minus L. So I just take that fixed big macroscopic guy, and then you look at ML. Okay? Or T star minus L, and you have TL, T1. Okay? And now, in this case, once you have done this, then the evolution of Q itself will be microscopic. Let me see, I have this written somewhere. Just 1 second. Where is my Q? No, this is the wrong one. This is the wrong one. Just excuse me. Yeah, here we go. So then you can write QL minus QL minus 1. So the change in Q, right, is going to be some matrix here, 0, 0, 0. And then you have this lambda over n minus V sigma VL over square root of n. So you take this rank 1 matrix and you raise it to the power. You conjugate it by T star to the L. Okay. So now finally this is an infinitesimal matrix. Okay. And you can show that as n goes to infinity, this evolution QL. So let's look at it like this. So Q NT T is in 0, T in 0, 1. As a process, it converges to some limiting process. Diffusion on matrices. And then once you have this diffusion on matrices, you have a kind of Brownian motion on SL2R. And if you look at that Brownian motion carefully, you can reconstruct this Brownian carousel object. Okay, let me see how much time I have. I have no time. Okay, so I will tell you two things before in my -5 minutes. So one of them is the following. There is a very interesting thing happening here. Actually, let me write down what this diffusion is. Okay, so this diffusion looks like this. Let's see if I can say that. Okay, so this diffusion on Q's. Okay, so let me write the limiting diffusion. Okay, so dq looks like this. So first of all, you have 1/2. There is this matrix I minus I 0, 0, and then lambda dt. Okay, so this is a kind of drift term, plus there is some constant. So let me skip that. So there is I dB dw bar dB minus I dB like that, and then this thing is conjugated. This whole thing is conjugated by some fixed matrix Z. This is essentially the matrix that diagonalizes T star. You see, because here you're conjugating by T star, you somehow expect something like that to happen. And then this is multiplied by Q. So that's what the evolution is. So right, so W is complex Brownian motion. B is the real Brownian motion. Okay, so essentially what it is just a Brownian motion in SL2R. Okay, so this with drift. So this is a BM on SL2R with drift. Okay, now what I'd like to tell you is the following. You remember that we had this evolution in which every step of the evolution you had a single noise term. Okay, you had the one noise term which was V2. And when you took a limit of this evolution, you got something which has these 3 different Brownian motions in it. You have this complex Brownian motion and the real one. So how did that come about? There is a kind of explosion of noise, right? You started with a one-dimensional noise, but in the limit you got a 3-dimensional noise. Of course, it's easy to see. It comes because of this conjugation. I mean, this noise you could think is pointing in some direction in the group, and when you conjugate this by T star, it starts pointing in all directions, and then you average, you get a higher dimensional noise. That's essentially what happens, and there are many examples of this. But why is this? Why many simpler examples than this one? But why is this important? So it's important because of the following. So we looked at the following thing. Instead of looking at this Anderson model on a line, okay, we looked at the Anderson model on a big box, on a long box. Okay, so it just looks like this. And it's very long in this direction. Okay, this is n, and then this direction is m. Okay, so the Anderson model in this long box can be solved kind of the same way as here. Okay, except all these matrices that I gave you, these are 4x4 matrices or 2x2 matrices. They'll be replaced by 2x2 block matrices, where the blocks will be m by m. Okay? But it's something very similar to what so you get something very similar like this, except all these guys that you see are matrices. And what happens? Well, when I solve my eigenvalue equation here, in every line I just get an m-dimensional noise. Okay. But because of this noise explosion, you get in the limit a kind of m² dimensional noise. Okay, so you start with an every line will have m different randomness, which has to do with the random variable written in the vertices or on the diagonal. But because of this kind of explosion, you get an m² dimensional noise. And that's why is that interesting? Well, that's kind of exactly the difference between the Anderson model and the random matrices, right? The Anderson model had only noise on the diagonals, so it had exactly m. If it's an m by m matrix, which is not exactly the case now, it had exactly m dimensional noise. Whereas the random matrices had m² dimensional noise. There was a noise in every entry. So in fact, using this noise explosion, we can prove the following theorem. This is now really a universality result. So universality in 1 plus epsilon dimensions. Okay, so as M, so there exists a sequence of ni, mi going to infinity, such that the spectrum, rescaled spectrum, of this model, okay, so this Anderson model converges to the sin 1 process. Okay, so this is the one. This corresponds to the GOE. Okay, let's maybe I'll stop here.